complexity. I will explain what is complexity, aspect ratio of your rupture zone, and the distance to your branch. This has 6 levels, and each level has 3 branches. So with the combination of all these parameters, we can create model 1, model 2, model 3, up to model n. And all these models can be used to study future tsunami, or in this case, we will be using them to assess the effects of past tsunami earthquakes. So now I'm going to delve a little bit into the seismological context of Chile. So Chile is located along a very seismogenic margin in the north up until Taitao Peninsula. We have the Nazca plate subducting under the South American plate, and from the Chile triple junction point in the Taitao Peninsula to the south, we have the Antarctic plate subducting under the South American plate. This accounts for at least 5 or so earthquakes with a magnitude of 8 or more every century, and 1 gigantic earthquake with a magnitude of 9 or more every 300 or 400 years. There is also historical data and records of Chilean earthquakes that can be traced back up until the 13th century from accounts from Japan, and up until the 16th century by Spanish monks and conquistadors. The Valdivia rupture zone has seen at least 2 gigantic, with more than 9 moment magnitude earthquakes in the past 5 centuries. This is the 1575 earthquake and the 1960 earthquakes. So this study centers on the Great Valdivia earthquake. It's the biggest earthquake in the recorded history. This earthquake ends a approximately 33 hours long sequence of earthquakes that started with the Concepción earthquake in the day before, the 21st of May. The rupture of the Great Valdivia earthquake spanned about 1,000 kilometers from the Gulf of Arauco up until the Taitao Peninsula, and it affected an estimated 2.5 million people in Chile and in other parts of the world, causing about 2,000 deaths. Material and infrastructure losses were valued at between 500 and 700 million US dollars. What is important about this earthquake? Well, I said that this was the biggest earthquake in recorded history. For this reason, this earthquake has been deeply studied and several source models have been computed, starting with the Barrientos and Ward in 1990, the Fujin and Satake in 2012, which uses tsunami and magnetograph data, and the Moreno et al. In 2009. This is an example of the rupture model from Moreno et al. 2009. This is the slip model, and this is the deformation model. You can see that the slip reached up to 45 meters, and the deformation went up until 12 meters. Now, I'm going to talk about the methodology of this study. This methodology can be divided into 2 distinct and successive sections. The first one is the model generation. The model generation using the logic tree approach. Start with the generation of slip distributions, and then these slip distributions are filtered using empirical relations, and with the remaining models, we compute the vertical deformations using the Okada 1985 solution. Then, with the restriction of the displacement models and deformation models, according to empirical relations and to deformation data, we can model tsunamis. First, with a low resolution model, and then we filtered those low resolution models using wave height data and historical accounts. Then with the remaining models that pass this filter, we will perform high resolution models in order to assess and filter with inundation data and more detailed data that I'm going to delve further in this presentation. And finally, with all these models, with all these restrictions, we will start the analysis of these models. The statistical analysis of the remaining models is based on the methodology proposed in Normaño 2021. It surrounds around the analysis of the logic tree branches and slip distributions along strike and along dip of the rupture of the displacement models. One of the things that Normaño proposed is the analysis of the models divided in segments along strike and along dip using their cumulative density distribution function. This is to say that for each segment of this rupture model, we will compute their CDF. Then we will analyze the virtual Mario graph wave height time series. And last, we will perform a comparison of the results with known and published models of the 1960 earthquake source models, such as the Moreno et al. 2009. So this is a summary of the software, of the methodology, of the numerical methodology that I'm creating right now. The main body of the software consists of 4 independent models. The first one is the one that generates the random displacement models and restricts them. The second one is in charge of modeling tsunami in low resolution and in high resolution and restrict them using paleo-tsunami data. The third one is the one that is in charge of automatically analyze these results. And the fourth one is a module for post-processing this data, namely to plot maps and plot time series, etc. These modules are designed to operate sequentially. However, and in this fashion, it can function in parallel with as many cores at the same time as branches in one level. This level can be chosen of the logic tree. So if one of the levels of the logic tree has 6 branches, we can perform random displacement models and generate random displacement models with 6 cores in parallel. However, each module can operate independently from each other in the case of one wanting to just generate random displacement models, or just performing tsunami modeling, or just using the post-processing tools for plotting maps or time series. So in order to do this, each one has a parent code that calls upon independent Python modules. And there's also a master code that calls all parent codes for sequential operation. So we have a master code, which calls upon the module 1, then module 2, module 3, and each module has a parent function that can work independently from each other. That depends with the Python module, and it's the same for each one. And this is a flowchart of the random tsunami source generation. First, we start with the generation of random slip distribution using logic trees, using the combination of parameters that we talk about. First, we assess if the distribution is smooth. If it's not, we discard the model. If it is smooth, we search if it complies with physical requirements, such as the ones proposed by Molina 2020, such as the gravity anomalies, frictional asperities, etc. If it complies, we compute vertical deformation, and then we test again. Does this vertical deformation comply with deformation data that we have? If it does, we model a low resolution tsunami. We test if it complies with wave arrival data. If it does, we model then a high resolution tsunami model to test if it complies with inundation and wave height data. In each one of these steps, if it doesn't comply with data or empirical relation or physical requirements, we discard the model and start again. However, if it passes all these filters, we save the model, save the branch parameters, and start analysis. This process is made for each and every one of the combinations of the logic tree. First, with the statistical analysis, we will perform an analysis of the displacement distribution along latitude or along strike, and the displacement distribution along dip or with longitude. Then we will divide the rupture zone in different segments following Normenio 2021. For this proposed methodology, and up until this moment, we are proposing 3 divisions along dip associated with lace domains, and 5 divisions along strike: north, north, central, central, south, central, and south. And for each one of these segments, we will compute the CDF. This CDF will then be compared with the known and published models of the 1960 earthquake. And also, we can compute virtual mariographs of the tsunami models. This is an example of the same slip or the same random slip distribution that I showed in the previous slide. This is the registered at the station 3, this one, from Moreno, from the deformation model from Moreno et al. 2009. And this is the result of the tsunami modeling using the deformation in the showed in the previous slide. The RMSE of both of these time series is 1.38 meters, which is not as good, but it shows that in what fashion we will be comparing these time series. So the hypothesis, the research questions, goals, and objectives. The hypothesis. The estimation of the most probable source model of the Valdivia 1960 tsunami, such as the slip distribution of the rupture, the geometry, and the rupture limits, obtained via analysis of random source models generated using a logic tree approach, will allow to achieve a solution that converges to and satisfies the available paleo-tsunami geodetic deformation and marograph-derived data. The research questions that drive our study are: is it possible to characterize the source of a tsunami, of a historical tsunami, such as Valdivia 1960, in the Chilean margin based on restrictions given by paleo-tsunami records, namely deformation data, marograph-derived data, diatom data, etc. And does a logic tree structure approach to generating random source models allows to converge to the source model of a historical tsunami? So these are the questions which drive the following research. The goals. The main goal is to estimate and characterize the source model of the Valdivia 1960 earthquake using a logic tree approach to generate random slip distributions and restrictions arising from tsunami and geodetic records. And specific goals is to implement a numerical methodology for the generation of random slip distribution models, then to generate these random distribution models, then compute vertical deformations using the Okada 1985 solution to the remaining models after filtering them using geodetic and deformation data. With the remaining models, to model tsunami in both low and high resolutions using models that comply with the observations, the remaining models that I talked about. And finally, to restrict tsunami models using the available paleo-tsunami data. At the end, we will perform an statistical analysis of the remaining models to study its convergence, or its degree of convergence, towards the known 1960 Valdivia earthquake source models. So now the expected results and progress made. Expected results can also be divided into two sections. First, there are software-related expected results. We will strive to create a suite of open source software for generating these random slip distributions using Python to automatically model tsunami, to restrict these models, both slip models, deformation models, and tsunami models with the available paleo-tsunami data, and to analyze statistically these results. And then we will strive to create an easy to use and intuitive user interface to work with, and to use this software with any historical or paleo-tsunami data with different types of available data. So this software, as I mentioned, is super flexible and accepts a lot of user input. And then, on the other hand, we have the expected results regarding the Valdivia 1960 source model. So we will strive to use the aforementioned software to study the Valdivia 1960 earthquake as a benchmark to test the capabilities of this software. We will try to use the available deformation and wave height inundation data gathered by Saavedra 2021 from the Valdivia earthquake as an input for the software, and then to test the capabilities of the software by comparing its results with known models, such as Barrientos, Fuji and Satake, or Moreno 2009. The progress made. All of these things that I will list up until now are completed. So we have all the codes for generating slip models. We have all the codes for computing vertical deformation, all the codes for restricting models using empirical relations, physical restrictions, geodetical and deformation data, and wave height and inundation data. We also have the codes for automatic tsunami modeling and codes for post-processing, as I said, for plotting maps, deformation, and slip, etc. All of these codes are available in GMT and Python 2.7. Why Python 2.7 and not Python 3? That's because one of the main modules and packages that this software uses was the moment of when I started, just available in Python 2.7. And in order to ensure compatibility, I had to do this in Python 2.7. This is an example of one of the scripts of the post-processing suite. The work schedule. So I divided this year in 4 trimesters. First my first task is to automatize tsunami modeling, which I already did. Then estimate wave heights and run up, apply restrictions based on paleo-tsunami records. I'm working on that. Then we have to make the final definition of the statistical analysis methods. As I said, we are basing our research on our menu 2021, but we want to improve on this regard and to apply more sophisticated statistical methods. And in parallel, I'm going to be modeling and generating random sleep models of the Valdivia 1960. And also in parallel, I will be preparing the manuscript of this work, my thesis. As a thank you, this project is being developed under the patronage of the Fondesit project number 111-80854, the source characterization for historical tsunamis of central southern Chile, and under CICLO, the Millennium Nucleus Seismic Cycle in Subduction Zones. Thank you very much.